the jump function parent graph. So jump function shifted 10 units to the right, so if that's 10, we have an open circle going that way at 1, and then going that way at -1. So the limit of this function as x approaches 10 from the right is 1. Obviously, it's discontinuous at 10, and it's because two things. The function value doesn't exist at 10. Those are both open circles. And because we don't even have a limit at 10. We have a limit coming at 10 from the right, but not an overall limit at 10. The second exercise is, what does that look like to you? A little bit, it's the difference quotient. Rather than h, they're using change of x. Rather than just approaching 0, it's specifically looking at 0 from the right. Regardless, this needs a lot of cleanup. So when we square, and this is going to be ugly because we're not using h, we're using change of x, but we're still going to square that binomial. X squared plus 2x change in x plus change in x squared. That's the binomial squared. Plus x plus change in x. Distribute your negative, minus x squared minus x. And then when you simplify, x squared minus x squared is gone, x minus x is gone, and the three terms left over all have a change in x in them. So we can divide each one by the change of x that's in the denominator. So that'll leave 2x plus change in x plus, what's change of x divided by change of x? 1. A lot of people tend to forget that 1. And then you realize once you get down this far that it doesn't really matter if you're coming from the right or the left. Yes? You can plug in 0 for the change in x and you get 2x plus 1. Can anyone tell what this is the derivative of? What the function is? Right here, right. Minus f of x. So if that was our f of x, x squared plus x. Oh, then we got this random thing in here, though. This is, if I'm doing f of x plus h. Oh, you're right. Yep. This is x plus h. This is f of x plus h minus f of x. So if I plugged in x plus h, I'd get x plus h squared plus x plus h. Yeah, good. So this is, and for those of you who know your power rule, which we'll get to shortly when we get to derivatives, you can check that. But anyway, I just was going above and beyond there. Our limit is just 2x plus 1. On the next one, this is not a one-sided limit. It's just a regular old limit. Coming at pi over 2 from the left or from the right would have to be the same thing for this to exist. Secant is the same as 1 over the cosine of x. So when you go to plug in pi over 2, what's the cosine of pi over 2? 0. And what's 1 over 0? Does not exist. What is the reason, knowing what you know about the graphs of secant, that this does not exist? Right, there's an asymptote at pi over 2. And I'm talking about that because it does say if not, explain. And then this last one is the greatest integer function wants to know our limit as we approach 2 from the right. Once we do that, I'm also going to explore what happens if we approach 2 from the left on the same function, because I think this is kind of an interesting function to take a look at. Thoughts? What? Well, what's this one? What's your guess? You think this is 2 or this is 1? It's just like a gut guess. Let's see. If I plug in anything greater than 2 from the right, like what? 2.5. So if I plug in 2.5, when you take the greatest integer below it. So if I plug in 2.5, I'm going to get 5 minus 2, which is 3. If I get even closer to 2 coming from the right, like 2.1, can you do that? I'm going to get 4.2 minus 2. Right? When I plug in 2.1, the greatest integer function on 2.1 is 2. And what's 4.2 minus 2? 2.2. Okay. What are you sold on the answer? So let's plug in something even closer to 2, 2.01. That'll give me 4.02 minus, if I plug in 2.01, what's the greatest integer function on 2.01? 2, 4.02 minus 2 is 2.02. Now are you sold? Or do you want to plug in something even closer to 2? Or are you sold on what the limit is approaching? It's probably just 2. If you want, sounds like you're confident, but maybe one more check would be peace of mind. 2.001 would be 4.002 minus the greatest integer function on 2.001 is just 2, and that gives us 2.002. Yes? Okay. So the answer coming from the right is 2. Coming from the left. See, Josh, when you plugged in 2.5, it's amazing how 2.5 is obviously close to 2, but in this context, that's pretty far away. So if we want to approach 2 from the left, we'd be better off plugging in something like 1.9 right off the bat. Mm-hmm. Only you know what you're talking about right now, right? Raise your hand if you follow what Josh is saying. Yeah, I know sometimes it's hard to put into words what you're thinking, but it's legitimate. I'm sure it is. 2 times 1.9 is 3.8. Minus, what's the greatest integer function on 1.9? 1. So that gives you 2.8. What if I plug in 1.99? That's going to be, well, I'm doubling 200 to get to 400, but then subtract 2, so it's 398. 3.98? And what's the greatest integer function on 1.99? Still 1. So that becomes 2.98. So do you get a feel for what this is approaching? 3. So I just want to show you what this looks like. So first of all, we've answered the question. It does exist coming from the right. It also exists coming from the left. It's obviously not continuous, though, at 2 because the overall limit doesn't exist. And if the overall limit doesn't exist, we can't talk about it. But let's 2x. I do. So here it is. And I'm going to change his window just to get a little bit closer in so you can see what's happening. This might be the first greatest integer function that we've seen like this, where the steps aren't horizontal, right? Any feeling as to what's causing that when you look at the function? I think it's the other x that's wrapped up in the calculation, okay? Up until this point, the only x that has been in the function has been the x that's within the greatest integer function. So the 2x is kind of changing, obviously. Something else is changing other than the value of this when we move around the x. So it kind of just still steps in a way, but they're not horizontal like we're used to, which is just sort of interesting. Okay, flip to the back. The limit as we approach 6 from the left. Do we want to plug in 6? Can't, right? The function's this function is definitely undefined right at 6 because you can't take the log of 0. But can you approach 6 from the left, like 5.99999? Sure. Natural log of 6 minus 5.9s is going to ask you for the natural log of 0.0001s, and that's only going to get smaller and smaller and smaller. So when you're trying to evaluate this, e to what kind of power equals tiny, tiny, tiny numbers. We talked about this yesterday. Huge negative numbers are going to yield teeny, tiny decimals. So this is negative infinity. From a graphing perspective, this is the same as negative x plus 6, agreed? And in order to do horizontal reflections paired with translations, you have to factor that negative out first. And the order in which you do the horizontal transformations is backwards, just like everything else is with horizontal transformations. So we're going to flip it horizontally first. Think about your log parent graph, which is here. We're going to flip it horizontally first here, so that the y-axis is still an asymptote, and then we're going to shift it right 6 units, which is going to bring your horizontal asymptote right 6 units as well, and the rest of your graph. So this is what we're looking at. So as we approach 6 from the left, we can confirm the negative infinity. And then on the last one, take a minute. What do you think about this? Raise your hand when you have question, a thought, an answer. Melissa, do you have a question, a thought, or an answer? Right, we don't have any continuity issue to really worry about here. The breaks are at 4. Something weird happens at 4 because you have a 0 in the denominator. So it's undefined at 4. It's also undefined at anything less than 4 because you'd have the square root of a negative, right? So our x's really can only be greater than 4 because of this part, which is a radical and a denominator. And then as far as logs are concerned, we can only take logs of positive numbers, so x can't be negative either. It can't be negative anyway based on the radical. So once we're greater than 4, there's no hiccups in the problem. No other places where we might have an undefined. So 5 is a perfectly continuous. So the fact that they say what's the limit as it approaches 5 from the right is kind of probably meant to try to trick you into overthinking it. So you just plug in 5 and you get the natural log of 5 over 1. So your answer is the natural log of 5, which is some weird decimal, I don't know. Okay, and then just in general, in order to be continuous on a closed interval from A to B, it has to be continuous everywhere in between. That's essentially what that first sentence is saying. And then the limit at the endpoint of A is never overall going to exist. So they just say that the limit as you approach A coming from the right. So picture something that's continuous from A to B. The limit as you approach the A value from the right has to equal the function value at A. Okay, there is no approaching A to the left here if we're talking about a closed interval. So it's the overall limit as you approach A doesn't have to equal f of A, because we're looking only at the closed interval, so we can't even look at the left. And then for the B one, they say if you're approaching B from the left, that limit has to equal the function limit. So when you look at these and you're talking about the continuity of this from -3 to 3, first of all, what happens at -3? What's the output? If you plug in -3, what's f of -3? No, yes it does. -3 squared is 9. 9 minus 9 is 0. Square root of 0 is 0. 3 minus 0 is... Okay. And then at +3, same thing's going to happen. You're going to get 3. What happens like at 0? 9 minus 0 squared is 9. Square root of 9 is 3. 3 minus 3 is... So we have this point 0, 0. And so in between there, are there any... does not exist in between? No. And what we know based on radical functions is that they kind of have that shape to them, where normally we throw arrows on the end, but here we don't. So this is continuous on the closed interval because it's continuous everywhere in between, because our limit as we approach -3 from the right does equal the function value coming from the right, and our limit as we approach 3 coming from the left does equal our function value coming from the left. In the last minute here, I'm going to show you B, which I've already done. This is interesting because knowing this graph, we know we have asymptotes at -2 and 2, but they only want us to look at the closed interval from -1 to 2. So is this continuous on the closed interval? Well, is it continuous everywhere in between -1 and 2? Yes. On the left endpoint, is the function value there equal to the limit as you approach from the right? Yes. On the right side of it, is the function value there equal to the limit as you approach that value from the left? No. So this one would not be continuous on that closed interval from -1 to 2 because of this side, because the function value over here doesn't equal the limit over there.
Good thing, Miss Right Hill.
Have a wonderful